I first met him and saw him several times in the US since. But my first very serious interaction in terms of physics that I remember started at a meeting in Budapest, which was really on charge density waves. But I was working on heavy fermions. And it's about that time that there was a paper by Volovic and Gorkov on classification of symmetries of superconductors in crystals. And buried in the results of this paper was that triplet superconductors cannot have nodes, line nodes of gap if there is spin-orbit interaction. And at that point, I was looking at and instigating experiments at Bell Labs, which were clearly showing line nodes in various transport experiments. And understanding and discussing with Lev led me to believe that these could not be triplet superconductors for this reason, and that the anisotropic superconductors that had been discovered had to be D-wave singlets, which then led me further to think about how you could get D-wave singlets and to antiferromagnetic fluctuations with Miyake and Schmidt-Ring giving rise to D-wave superconductivity. At the same time, we had a number of letters exchanged. We didn't used to have email those days, in which we were discussing the Fermi Liquid renormalizations in heavy fermions. And there was a lot of discussion that the Fermi Liquid renormalization in heavy fermions are completely different for Fermi Liquid renormalizations in liquid helium-3. For instance, it used to be considered a crime among the Landau school to mention the quasi-particle renormalization amplitude in relation to any thermodynamic properties. Landau theory was meant to say that those things, the beauty of the theory is that all that microscopic information will never appear in low energy transport or in any thermodynamic experiments. But in heavy fermions, it looked like when we were measuring the specific heat, we were measuring 1 over the quasi-particle renormalization with lots of other attendant renormalizations, which followed from that. And although various people were telling me that, that it's impossible, when I talked to Lev, I realized that, that orthodoxy was not necessarily true, and that helped me a lot. In this long period from about 2000, I have a whole bunch of correspondence with him discussing various aspects of cuprate physics. On this problem, he started, in fact, calculating how anisotropic pseudogap might arise in a Q equal to 0 ordered state of a certain kind, which I favor if they're domains. And my last communication from him on this issue is, I looked up my notes, it's all the way to September 2016. This is what I also had a lot of interactions with him on. Can one decipher effective interaction from experiments when there are no small parameters so that no calculations can be reliable? Or as I will explain to you, discussing what it means, what does an irreducible interaction mean? What is the physics irreducible interaction? So I've decided to talk about this stuff because in many ways this is an interaction. What I'm going to talk about is the intersection between the Landau School of Physics with the Bell Lab School of Physics. Both of them are gone now. It's conceivable that the Landau School might come back, but the Bell Lab School never will. Don't we all long for the days of the Cold War? how wonderful it was compared to what it is now. So what I'm going to talk about is to what extent do methods of quantum field theories in statistical physics, as in this great book by Abrikosov, Gorkov, and Zaloshinsky, help discover physics beyond quasi-particles in superconductivity in cuprates, heavy fermions, ion-based compounds, etc. And this thing boils down to asking about the nature of irreducible vertices and the validity of the Eliashberg equation. What do I mean? Well, here are a bunch of truisms which you can find in AGD, that any response function, and that's what we are interested in, any response function can be expressed in terms of the total vertex and the exact Green's functions. And if you have the exact Green's function, you need to know the self-energy, and the self-energy can be expressed in terms of the exact vertex as well. So the truism is, if you are looking for singularities, which you need if you have to break down Fermi Liquid, you need to be looking at the singularities in this total vertex. But let me put it slightly differently, which is based on a crucial step in AGD derivation of Fermi liquid theory. And the derivation says, quite obviously, that you can write down the total vertex in terms of an irreducible vertex, and then an irreducible vertex infinitely repeated with particle hole sections. This object is a horribly complicated object. It includes every diagram that you can conceive of, except from diagrams that can be broken into two parts by cutting a particle and a whole line and channel, which takes Q. So it's the most horrid thing in the world that you can think about, and that is what you work with. So how to break a Landau Fermi liquid? Well, let's see. What is a Fermi liquid? In Fermi liquid theory, and that's the starting assumption, the irreducible interaction, which in effect is interaction between incoherent parts or interactions at high energies, Landau theory assumes that this is completely regular. And in fact, the forward scattering limit of this irreducible interaction can be used to get your Landau parameters. Now, if this irreducible interaction is completely regular, then the only way to break Landau Fermi liquid theory is through this repeated scattering, repeated particle hole scattering. And that's the physics, for example, of Pomeranchuk instabilities. It is also the physics when you are at large Q and you have charge density wave and spin density waves, and you cannot use Fermi liquid theory and you have to do actually calculations. This is what people have been doing. The skeletal structure of all that stuff is generalized RPA. The whole Moria, Hertz, whatever you call it, is really based on generalized RPA. Now, there is an alternate way to break Fermi liquid theory, which I happen to favor, which is that the irreducible vertex itself is singular, and not just in the forward scattering limit. If that is so, that's quite a different ball game. Now, in my talk, I'm not going to proceed in the historical manner of why one might think of that as the basic physics in the cuprates. I'm going to adopt the inverse approach and show that a particular singular irreducible vertex dominates the physics of the cuprates, but deciphering the vertex from the experiment using AGD's methods. And then I'm finally going to say, if I have any time, that the methods of AGD themselves cannot be used to generate that irreducible vertex. Now, I had written down the self-energy in terms of the total vertex, And that turns out to be not a very useful way of thinking in this context. There's an alternate way of thinking of the self-energy, and this is also an identity. This identity occurs in a by-the-way fashion in AGD, that the self-energy can be written exactly in terms of the irreducible vertex and the exact Green's function. And this comes in by the way in the process of deriving Fermi liquid theory, where you assume that I is completely regular. Now, if you look at this, you notice that this has the same skeletal structure as your calculation of the self-energy, provided two things happen. There's no singularity in this channel, and that this vertex is only a function of omega minus omega prime. So there's some kind of collective fluctuation dominating the physics. Then the structure of this is the same as this. And this is true even if the irreducible vertex is singular in this channel containing omega minus omega prime. Okay? This can be generalized slightly to say that if you're looking at the pairing self-energy and you have the anomalous or the F part of the Gorkov Green's function, if you have an irreducible interaction in the particle-particle channel, and again, if the same two conditions prevail, this is also an identity. Now, if you have this and this, and those assumptions on the irreducible vertex are fulfilled, then these two equations are at a skeletal level identical to the pair of Eliashberg equations. Okay, these are the Eliashberg equations. So, if you can extract sigma and delta from experiments, and you put sigma and delta in the normal and the anomalous Green's function, you can deduce the irreducible vertex in principle as well as the quality of the experiment. And then you have to make sure that those assumptions about the irreducible vertex are correct. In other words, you do not need anything like the Migdal approximation to deduce the irreducible vertex and therefore the total vertex purely from experiments. And this is the task I set myself to do by engaging fantastic experimentalists. What this needs is fantastic experimentalists. So let's go back to a pair of fantastic experimentalists, McMillan and Raoul in 1965. And you might remember that the experiments that John Raoul did, tunneling experiments, as interpreted and analyzed by Bill McMillan, is the most definite evidence that superconductivity in metals like lead is from electron-phonon interaction. You get the ratio of the conductance in the superconducting to the normal state. From that, you deduce the pairing self-energy, from which you deduce the fluctuation spectrum, which led to pairing, and then you can compare that to phonon spectra measured independently. Unlike common belief, including belief of Bill McMillan, these results do not depend on the validity of the Migdal approximation. That's what I'm contending. But in the case of the electron-phonon problem, there's a luxury. There's a luxury which allows you not thinking deeply about the problem, because they had a small parameter, which is 10 to the minus 2. So the Migdal approximation was valid. So one never had to think in this direction. But in the case of cuprates and iron compounds, you will see that one has to. Let me tell you a little story here that Bill McMillan told me within months of my joining Bell Labs. He had just returned a year ago or so from the Soviet Union in one of these Soviet Academy meetings that used to happen that Patrick told you about. And he came back and he said, I gave a talk there, and there were these Soviet physicists like Gorkov and Kalatnikov, and they were asking each other and to other American physicists, is this guy McMillan an experimentalist or a theorist? Okay? And of course, Bill was absolutely thrilled at that he could be taken for an experimentalist. Okay? Whereas my guess is that the Russian school meant it in a slightly different fashion. So I'm going to be the experimentalist here, and first say that there was a proposal made on how you could decipher the nature of pairing in the cuprates by Ilya Vector and me long ago. And first thing to say is that ordinary tunneling is not useful for D-wave superconductors. Raoul McMillan methods are not useful, even besides the experimental technical problem. The issue is that the normal self-energy has the full symmetry of the lattice, and the pairing self-energy has the symmetry of the pair, D-wave, if it's a D-wave pairing. And therefore, to decipher anything from experiments, you need a resolution in angle. Okay? You cannot integrate over all directions. So you have to do angle-resolved photoemission. And in principle, then, they are not just one Eliashberg function. There are a pair of Eliashberg functions, one in the S-wave channel, the full symmetry of the lattice channel, and one in the subgroup, the D-wave symmetry channel. To do this, as I said, needs a very good experimentalist, because while Bill McMillan and John Raoul in the tunneling experiment in lead had an accuracy of 0.1% in the relative spectra in the superconducting and the normal state over energies of the order of twice the phonon energy and temperatures from 20 degrees down to 2 degrees or so. What we need here is high accuracy or an energy scale of half a volt, varying in temperature from above 100 degrees to low temperatures. And that is very, very hard, even with modern tools. But the best ARPIS data in the world is being available in Jingjiang Zhao's lab in IOP Beijing. And I've sat there and taken data. And even there, the machine works only about 20% of the time. Okay? It's a very, very hard experiment. But you can so what you do is you take the spectra as a function of energy and as a function of momentum. And here is, let's say, the spectra at 100 Kelvin going down to 17 Kelvin. At 100 Kelvin, it's flat. At 17 Kelvin, you begin to see some stuff. And you know that at high energy, about 0.3, 0.4 eV, nothing interesting should happen. And you then look at the noise in the data, and that noise, the precision of the data is 1%. And what you need to do to analyze experiments is to look at this region and see changes better than 1% and try to deduce things over a range of temperature and over a range of angles. So you get this kind of quality of data. You fit this data, okay, and you fit this data. This is how you fit it, and you measure it at different angles, and you solve the generalized Eliashberg equations to deduce first you measure the self-energy, the normal self-energy and the pairing self-energy, and then you solve the integral equations. So first thing you do is the normal state. You do laser ARPIS, so you cannot go through the whole Brillouin zone. So you're looking at from diagonal direction to about 25 degrees from it. And you measure the self-energy in the normal state, both its real part and its imaginary part. And you notice that the imaginary part up to 0.2 eV or so is linear in energy and is independent of the angle as to where you look. So the imaginary part of the self-energy is nearly angle independent below an angle dependent cutoff, and it's linear in energy. Incidentally, these two conditions are necessary and sufficient to give you linear resistivity. Okay? you look at the evolution of the normal self-energy below Tc. So here is the same self-energy plotted at a particular angle at high temperatures, 90 K, just above Tc. And you notice that it's not completely really linear. There's a tiny bump here, and this bump has been a bloody nuisance, and I'll talk about it. And then you go into the superconducting state, and you see superconductivity-induced features. But you notice that this self-energy has the full symmetry of the lattice. It's angle independent because we can measure it. Okay? And above the superconductivity-induced features, it's again linear in omega. You now can invert the Eliashberg equation, and this is still the normal state, and you get the fluctuation spectra. And I'll tell you precisely what I mean by the fluctuation spectra, what we call the normal Eliashberg function, which is angle independent in this whole energy range, except for a cutoff, and that cutoff seems to be very closely related to the bottom of the band with respect to the Fermi energy. And then there's this bump. This bump from this lack of linearity appears. So the spectrum is angle independent. It's frequency independent, except for this cutoff and this bump. And in this range, there is this constancy to it in energy and constancy to it to within our accuracy in angle. Okay? Then you go to the harder part, the pairing self-energy. So pairing self-energy is much harder because it is coming from the change in the self-energy going from the normal state to the superconducting state. That's where you need your greatest accuracy. And then you measure it as a function of angle, and you discover that within our accuracy, it is going as cosine 2 theta at the angles measured. And very nicely, it changes with temperature. It increases the imaginary part and the real part that are deduced change. And here it is. If it's frequency dependent, it's very weakly frequency dependent, the pairing self-energy, and it increases below Tc. Because of the experimental noise, the data is not useful about 0.2 eV. But there's at least a cutoff on the scale of 0.2 to 0.4 eV in the problem. So what are the fluctuations that give rise to high Tc? First, let's look at this normal Eliashberg spectrum, which has the full symmetry of the lattice. That was like that at 90 K and at 70 K. And if you look at the fluctuations which give you pairing, and by T tilde, I mean you have divided it by cosine 2 theta, that thing is like that. It's just like the normal state spectra, the normal fluctuation spectra, except it does not have a bump. That bump is something else which is not attractive in the D-wave channel. Okay? Now, okay. So what I've been talking about, En and Ep, they are nothing but related to integrals over the irreducible vertex in the normal channel and in the pairing channel. And in the pairing channel, there's a k prime, there's a cosine theta k prime, and this we measure is going as cosine of theta k. Okay, so we have all the information we know about it. All this experiment is done quantitatively, so we know these numbers, we know the coupling constants in various channels, and so on. Two important questions come from these results. What model gives such fluctuations? How can the same fluctuations which give nearly isotropic scattering in the normal state give you D-wave pairing? Actually, both these questions were answered earlier, and it is not the purpose. That would be another talk. It's not the purpose of the talk to go into the theory behind it, because I'm acting as a Bill McMillan wannabe. I'm only going to talk about the experimental results. But let me just state that the fluctuations are from the topological excitations of the distributive quantum XY model, which can be essentially solved exactly. They cannot be derived by AGD techniques. And the model for which this XY model holds is this model of discovered experimentally in the cuprates following suggestions from me of the loop current order. And the answer to the second question is related to the fact that the fluctuations, the angular momentum fluctuations, the rotors, and if they are angular momentum, the rotors, they will give you in the S-wave channel and repulsion, and in the D-wave channel interaction. Okay. Since my chair is standing, let me say that these fluctuation spectra that I'm talking about is of this form, and the most important part of it is this omega over T scaling and the Q omega dependent separable. And one of the great pleasures was have Lev look at this paper with a tooth comb and ask me various questions. And I really, really liked the fact that he said, I think I now understand how this thing is working. It's a fundamentally new approach. I don't know. Never believed such an analysis could be possible. And then he gave me various suggestions. In fact, my last communication from him is on February 25th, 2016. I want to close with something else. On Lev's 75th birthday, some of us were rewarded by a book of sketches that he made all through his life, which contains various characters, some hidden and some not so hidden, from the Landau school. And the one that is absolutely not hidden is Lev's picture of Landau drawn in 1961. Here's Landau staring at a famous quantum electrodynamic diagram with various other things going on. And you begin to realize and to wonder that here is Soviet Union in 1961, and here's Lev Gorkov drawing a sketch of a very highly respected, beloved figure being drawn by this stern-looking man who, from the picture that we saw earlier from Mineev, was looking even sterner and more upright in his youth. And what kinds of things were going on in his mind, and what a person he had to be to create a book which seems to be illustrations of Master and Margarita, if you know the book that I'm talking about. And so Lev was a character who could, long before Master and Margarita came to the public notice, understand life in that fashion. Thank you.
Thanks, Chandra. Some questions?
Chandra, do you need any frequency dependence that you can't get from photo emission? In other words, what about the inverse photo emission part of omega? Does that enter in trying to decode the vertex that you need and the self-energy? Or in other words, what do you do about that part of it?
I think if, given our total belief in detailed balance, I don't think it's required.
I see.
Of course, with the assumption of particle-hole symmetry of the band structure,
but
okay, in that range, which may or may not be true. But other than that, I do not think that's an issue.
I
Certainly,
I
Bill
think-
McMillan never required.
No, electron phonon, we had that symmetry under very good control, although they did have that data because, of course, they could tunnel and observe either positive omega or negative omega.
Yeah.
The problem here, I think, is if you look at some of the tunneling data,
Some of the what?
tunneling data on the cuprates, there appears to be an asymmetry with respect to omega that we didn't see in the, say, lead behavior. And so I'm wondering whether that causes you a problem because
No,
even
my
with your marvelous way of going for things, you don't have the inverse photo emission data.
My point of view on that is that will make quantitative corrections, but nothing in the overall physics.
Question or minor comment about the very beginning of your talk. When you separated, can you hear me?
Now I can hear you.
Okay, I'll try to be this way. At the very beginning of your talk, you separated the Pomeranchuk transitions from the new stuff which is related to singularities in irreducible vertex, right? This was the beginning of your talk.
No, I think of Pomeranchuk instability as really coming directly from particle-hole scattering.
They do come from particle hole, but consider
Nothing from the irreducible vertex.
wait. Consider Pomeranchuk instability in dimensions 3 or smaller.
In
dimensions 3 or smaller. Effective mass diverges at the transition. You can check it in direct calculations. Divergence of a mass means that corresponding Landau parameter goes to infinity.
Sorry, what do we mean by effective mass here now?
M
The
star?
mass that appears in specific heat?
Yes, exactly. All I'm trying to say is that if you look at this divergence through the eyes of Fermi Liquid theory, you will see this is due to divergences in irreducible vertex I. So what I'm trying to say is that even conventional Pomeranchuk transitions, if you consider them in dimensions where effective mass diverges, are also corresponds to the fact that one of Landau parameters goes to -1, while other parameters diverge. And these are divergences coming from I, from irreducible vertex. So I don't see that what you are saying and what I'm saying are completely contradiction.
We'll have to discuss it further. I don't see irreducible vertex playing a role in those instabilities.
Anybody else? Okay, let's thank Chandra again.